Alright, so if I have 12 volts applied through a switch to a capacitor, and suppose there is a resistor right next to it. When the switch is on, immediately this picks up 12 volts, right? When the switch is on, immediately the capacitor charges to 12 volts. And then the resistor is there to discharge. So the moment I connect the switch for a moment and then release it, I'm going to have this capacitor beginning to discharge through the resistor. Now if the resistance is 2 mega ohm and the capacitance is 2000 microfarads. So the capacitance is 2000 microfarads and the resistance is 2 mega ohm. Let's find out this. Find how much is the time constant. First find how much is the time constant. Next, let's say a relay will be active till the voltage reaches 5. Below 5, it is not going to be active. So let's find out how much time it takes for the voltage to go from 12 to 5 volts. Because from 12 to 5 volts, the relay will be actively clicking. And once the voltage goes below 5, the relay will release its voltage. Understand what I'm saying? So it will make the contact until the voltage reaches 5. And below 5, it releases the contact. It's not strong enough. The electromagnetism is not strong enough to hold it there. So once it reaches 5 and below, it releases it. So go ahead and find out the time constant first. And then find the time it takes for the voltage to drop from this to this. How do you find the time constant?
Multiply the capacitance by the
RC. Time constant is RC. So multiply 2 mega ohms times 2000 microfarads, which is 4000 seconds. So 2 mega times 2000 micro. And the answer is 4000 seconds. Time constant is the time taken for a capacitor to discharge to 1/8 of what it was before, correct? And so it takes 4000 seconds for this capacitor to drain from 12 volts to 12 divided by 2.718, which is 12. Oh, thank you. So that is the time constant. So what are you going to do now? I'm taking this off for space. What you're going to do now is use the voltage is equal to voltage naught e to the power of minus t over RC. You know, the charge and the voltage, they go along with each other. So Q is equal to Q naught e to the power of minus t over RC. And the same applies to voltage because Q is equal to CV. If Q is varying in a certain fashion, V has to vary in the same fashion. So this voltage is also applicable. So 5 is equal to 12 times e to the power of minus t over 4000. That's your equation. What do you do now? Once I put this video through, you just follow the video, it should be all clear. Okay. Alright, so 5 divided by 12 is equal to e to the power of minus t over 4000. And then flip the whole thing, so 12 divided by 5 is equal to e to the power of t over 4000. So 2.4 is equal to e to the power of t over 4000. The only way to bring a variable from the power to low down here is by taking the logarithms. But in this case, because it's e, we take the natural log. So when you take the natural log on both sides, whatever it is, log 2.4, Ethan, how much? What is log 2.4?
0.8.
Length, natural logs.
Yeah. 0.875
is equal to T over 4,000, and then it is len E, which is 1. And then you can figure out the time. Time is equal to 4,000 times 0.875, which is how many seconds?
3,500.
Almost 3,500 seconds. That's close to a minute. Oh, an hour. It's close to an hour. 3,500 seconds is a lot of time. So what's going to happen is that capacitor is going to hold the relay on for approximately an hour and then release it. What made it delay that much is the value of 2 mega and 2000 micro. That made it. Now, if this was not 2 mega but 2 kilo, what is the time constant? Just 4 seconds, which means it's going to hold on to roughly 3.5 seconds. That's it. So, yeah. Time constant is like 4 seconds, which means around that time, that's what the relay is going to be on. So it's not going to be on for more than 4 seconds. Okay? I use this RC sort of technique when I joined teaching and I had nothing but just 2 bedrooms, and I used only 1 room to stay because that's a lot of things for me. I don't use the kitchen almost. I don't use anything else. I just stay in one place. So I needed a calling bell, and I didn't want to go and buy a calling bell and spend money on it. So instead, what I did was I took a birthday card, or the Christmas card. You open the Christmas card, it will sing Jingle Bells. It was the same tune, Jingle Bells. So open the Christmas card, it sings, and close it, it shuts off. So I took that board from there, and I used a little amplifier made up of a transistor and a resistor and a capacitor. So a tiny amplifier, the smallest amplifier you can ever think of, and then a speaker. And I put that one with the switch outside the door. It worked as a calling bell. But the problem was, when the calling bell is pressed, or if it is pressed and kept pressed, then only the song plays here all the time. So normally when someone is ringing the calling bell, it will be like one push. So it will be like jing, that's it. The whole jingle bell is not coming out. So it's a little pulse, and that is not enough to wake me up or to realize that somebody is waiting at the door. So then I said, okay, the only thing to do is to put a timer, a capacitor basically. So when I put a capacitor to the circuit, so if anyone touches the switch, once, even one pulse, capacitor charges fully well, and then I can set up a delay according to the choice of resistance capacitances, right? And I chose a delay of roughly like 10 seconds. I made it 10 seconds. Almost time constant was 10 seconds. So the relay was held for that much time and then goes off. Okay? So the calling bell worked fine after that. Like one press, the jingle bell song will go on to exactly 10 seconds. Exactly the right place it turns off. It doesn't actually go any further exact because it all depends on R and C. So as I said earlier, the timer or the time delay, this is basically the brain behind any timer circuit. Of course, it can be used for constructive uses, as you can see in multiple places, and there are destructive uses as well of the timer. Okay, so constructive uses, you can set a certain device to come on at a certain time or go off at a certain time. That's a timer. Countdown timers, right? The stopwatches, basically. They're all like, even in your stopwatch, even in your watch, there will be a small capacitor. Have you seen that capacitor? In a digital watch, if a digital watch is broken, just open it up, and you'll see a cylinder there inside. If you noticed it. There will be a tiny cylinder. Everything else is not, everything else is like integrated circuit and all that. But there's one tiny cylinder, which is basically the brain behind the timer. So the whole clock works on that. Anyway, so capacitors discharge and charge at a certain rate depending on this thing called time constant. Now let's talk about Now, some of the things that you have already done last year is about the resistor, ammeters and voltmeters, right? You've done it. Just to brush it up. What is an ideal resistance of a good ammeter? 0. The resistance of an ideal ammeter is supposed to be 0 because the inclusion of the ammeter into a circuit is not supposed to affect the resistance of the circuit. Therefore, it has to be 0. So if a current is already flowing in a circuit and you want to detect it, you must put something that does not take any that does not include any resistance to the circuit. Because if it has its own resistance, then it will disturb the very current that it wants to measure, right? Now, what is an ideal voltmeter supposed to be? Infinite resistance. So we've gone through them last year. So you must just understand. So ammeters are always connected in series and voltmeters are always connected in parallel. But realistically, ammeters do have some resistance and voltmeters do have some resistance. Do have a resistance, not infinite. So a voltmeter can have a 10,000. If it's a digital voltmeter, it's going to be around 10 mega ohm. That's not infinity in one way. Okay, and if it's a 10 mega ohm voltmeter, will it read the real voltage? Depends on what you're connecting it across. For example, if I have 10 volts connected across a resistance here of 2 mega ohms and the resistance over here of 3 mega ohms. How many volts is supposed to be across here? Rick? How many volts should be across here? You don't have to do calculations for this. Just look at it and immediately you should be able to say it. Huh? 10 is what is supplied to both of them.
230 milliamps.
So how many volts will this voltmeter read is my question.
1030 milliamps. 1030 milliamps.
6 volts. How did he get 6 volts?
They're in series loops.
Yeah, so what's happening is this 10 is going to be distributed, some here and some here. And both are mega ohms. So it's going to be evenly distributing it. So this 10 volts is going to be split into the ratio of 2:3. So what is this going to get? 6 volts. One way of doing it. Other way of doing it is sit and calculate. 10 divided by 5 mega ohm. What's the current? Use a calculator. 10 divided by 5 mega ohm gives you 2 microamperes. 10 divided by 5 mega ohm will give you 2 microamperes. Multiply that current with 3 mega ohm and you'll get 6 volts. Right?
Yes.
Now, I want to measure it with a voltmeter. So the best voltmeter I could lay my hands on is a digital one. So I'm going to connect a digital voltmeter here. But this digital voltmeter has its own resistance of 10 mega ohm. Now comes the issue. The current that you calculated earlier was going here, right? How many amperes? The current that was going here before is 2 microamperes. Now will the 2 microamperes continue to go here? No? No, because it comes over here and looks at 2 different routes. Like this is 3 and this is 10. It can't just ignore the 10 and go completely here because 10 and 3 are pretty close, right? So what will happen is more current will go here and some current will sneak through here, which means the current through the 3 ohms is reduced. That means the potential difference across the 3 mega ohm is no more 6. It's going to be less than 6. So this voltmeter will read a voltage which is slightly less than 6. Not slightly, majorly less than 6. So if a voltmeter has some resistance, this is the consequence. It won't read the right stuff. It won't read the real voltage. Can you tell me what the voltmeter reads now? How do you find out the reading of the voltmeter? Tell me the reading of the voltmeter. If this was a very ideal voltmeter with infinite resistance, then it would have read 6 volts. Now it is not an ideal one. Look at this, 10 mega ohm. Yes, it is a big resistance, but you're comparing with this now. So it is not that big. So how do you start this calculation point? You need to find this current. First, you have to find this current. Now, is the current 2 microamperes?
Yes.
No.
It's changed.
There's changes because now you have to do the calculation once again. What is the total resistance in this circuit? The total resistance in the circuit is made up of 2 resistors in parallel added to 1 resistance in series. So you got to work this out. What is 3 and 10 in parallel? What is supposed to be the equivalent resistance of 3 and 10 in parallel?
2.307.
How much?
2.307.
Okay, so this is 2.307, just keep it like that, and mega ohms, right?
Yes.
This is 2.307, just product over sum. 3 times 10 over 3 plus 10. So 30 divided by 13. That will be 2 point whatever he said. Now what is the total resistance in the circuit? Plus 2 mega ohms, which is 4 point. 4 point. So let me put the number down. Let me put those numbers down here because we need them. What's the equivalent resistance of this?
2.308.
Mega ohms, right? Now what's the total resistance? 4.308. So what's the new current? It is 10 divided by 4.308 mega. So what is it going to be? 2 point? 2 point?
3, 2, 1.
I'll leave it as it is. Don't round off any numbers at intermediate stages in a problem. Keep it as it is. Don't worry about 6 fixing. 10 divided by 4.308 mega is 2.321 microamperes. Now that is the current that's coming here, 2.321 microamperes. Now to find the voltage across here, multiply that current with this. That will tell you the voltage. So multiply 2.321 microamperes with 2.308 mega ohms.
5.357 volts.
Almost 5.36 volts. Look at that. It was supposed to read 6, but it goes and reads 5.36 volts because this is not really infinite. Yeah? But will this voltmeter be a good voltmeter for resistors that are in kilo ohms? Yes. It will definitely be good. Let's work it out in kilo ohms now. If I'm going to say this is 2 kilo ohms and this is 3 kilo ohms, now let's work this out once again. If this is 3 kilo ohms and this is 2 kilo ohms. If the voltmeter is not brought in, how many volts is supposed to be there? What should be the voltage across here? 6. It's supposed to be 6. Now, when you put this here, what's going to be the equivalent resistance of 3 kilo and 10 mega? Or you can call it 3 kilo and 10,000 kilo. So it's basically between 3 and 10,000. So the product of 3 and 10,000 divided by the sum of 3 and 10,000.
It's about 3,000.
How much?
It's about 3,000.
No. This is 3 kilo and this is 10,000 kilo. So I'm putting the same case so you'll know how to do it. So what is the equivalent resistance of this? It is 3 times 10,000 divided by 3 plus 10,000. How much is this?
2.9.
2.99
Yeah.
goes on like that.
2.9.
So it's almost 3. 2 point?
999.
Okay, let's keep it like that. Milliamperes. Correct? Because now it's kilo. They're all in kilos, so it's going to be milliamperes. So this current is going to be 2.9991 milliamperes. Now that current flowing through,
That's the.
wait a minute. So 2.9991 kilo ohms, right? Now what is the current? So 2.9991 kilo ohms. What is going to be the current?
You didn't add it.
You didn't add the two.
So it's 4.
Oh, I didn't add the 2, so 4. Good. 4.
Two,
So it's like 2 point.
0, 0, 0, 4.
How many zeros are there?
There's 3 zeros and then
And then a 4 milliamps. So this current is going to be 2.0004 milliamps. Now multiply that with this, because this is the equivalent resistance here. So 2.9991 kilo ohms is the equivalent resistance. Multiply those two, you should be getting
5.9999.
Yeah, so 5.9993, which is as good as saying it is reading 6. Okay. So, depending on the resistance used in the circuit, you can decide whether this is considered as an ideal voltmeter or not. Depending on the resistors used. If the resistors that are used in the circuit is like mega ohms, then this voltmeter is not good. It's not going to do a fair job. But if the resistors involved are in ohms or kilo ohms, this is a good voltmeter for using it because it is almost reading 6. Make sense? So Kirchhoff's laws. Since you've done it last year, you must be quick to understand this. So for the first law, the summation of all the currents at a junction is equal to 0. That's what it is. So if you have currents coming into a junction and currents going out of a junction, if you call them as I1, I2, and I3, and I4, and I5, according to this, the algebraic sum of the currents coming into the junction and going out of the junction is equal to 0. Why that rule is true? Because charge is conserved. So since charges are conserved, if some number of coulombs are coming in per second, the same number of coulombs must exit. You cannot have charge accumulated somewhere. And that is why this rule. So all the incoming currents is equal to the outgoing currents. That's the first law. So we will use Kirchhoff's laws, and we've used it so many times before. If a current of say 5 amperes is coming here and entering this resistance and this resistance, if a current of 2 amperes goes this way, and immediately you conclude that this is 3 amperes, and that means you're already using Kirchhoff's first law. So the conclusion that you do here, that this current must be 3, is because you know that the incoming one is 5 minus 2 minus 3 should be equal to 0. That is the first law. Okay, you have it. If you check back in your notes, you must be able to see them. And the second law needs to be taken care when you work through problems. The second law says the sum of the EMFs plus the sum of the potential drops is equal to 0 in any closed loop. In any closed loop, in any closed circuit, that should be true. And that is an important rule. So a closed loop, meaning it's a completed loop. So when you have a closed loop like this, there are some EMFs, there are some resistors, You may have internal resistance as well. This is a closed loop. You can have multiple closed loops. You can have another loop here. That's also closed loop now. How many closed loops do you see here?
3.
3. One closed loop, second closed loop, a big closed loop. So we have closed loops, and for each closed loop, this rule is true. So when you apply the rule, we need to take care of some sign conventions. So let me remind you about sign conventions. So sign conventions. When you search for EMFs, when you're searching for EMFs, first of all, how do you search? You got to go around this loop in any direction you choose. You need to choose which way you want to go. So if you decide to go, say, clockwise, starting from here, if you decided to go clockwise, then to search for EMFs, you don't need to know which way the currents are going in the circuit at all. The EMF's directions are all decided by the terminals, polarities, that's it. Nothing to do with current. Which way the current is going into the battery, is it in or out? None of your business now. Right now, for EMFs, just forget about any current at all and just focus on which way are you going. You're searching that way. When you're searching that way, which EMFs will you consider as positive? If you bump into the positive terminal, then that's positive EMF. If you bump into the negative terminal, there will be negative EMF. So for this loop that I've chosen, when I start from here, that's a positive EMF, so E1. And then I keep searching, look for only the EMFs. When you come here, this will be a negative EMF. And then you come back to the starting point over. So this is how we search for the EMFs. And to search for the currents, which way is the current going to be, is purely your guess. So before starting off with any question which is kind of tough, you just guess your directions first. Just guess your directions. So which way do you think the current is going to flow? Well, it depends on E1's magnitude and E2's magnitude also, right? So let's say this is pushing a current this way. Let's call this I. And what's happening with the I, it comes here. And let's say this is also pushing a current like that. And so the I2 is here. And this is I1, let's say. And this is I. You can call them like this. When you're deciding these currents, you can label it anything you want. X, Y, Z, I1, I2, I3, or I1, I2. It's purely your choice. Which way are you going to mark the currents? Purely your choice. So I chose to make the current go this way because it makes sense that this is like this. Alright, Jay? And when it comes here, this one is going to make a current go this way. So therefore that is I2. But when these two come to this junction, according to the first law of Kirchhoff, it's going to be I1 plus I2 going this way. So we already taken care of Kirchhoff's laws. Number one, Kirchhoff's law number one, we already taken care of. So what is this I? I1 plus? So I don't want to write even I, because if I introduce I, then it will be 3 variables. Now if I don't introduce I, there's only I1 and I2, and I1 plus I2, there are only 2 variables right now. So that's good. So this is your first action, and of course you have to mark this current everywhere, so that you will not make a mistake. What's the current here? What's the current here? I1 and I1. So keep marking all those currents everywhere so that you won't make a mistake later on. Especially before resistors, you put that current value. Before it enters the resistance, you put the I. Okay, so that you will be reminded about that. Alright, so now the next thing to do is to look for the potential differences. Now, potential difference depends on which way you're searching. Now, if this current is going in this direction, which end of this is positive? the entry is positive and this is negative, right? The current enters and leaves. So wherever the current enters the resistor, that side is higher potential and lower side is here. So we have the potential difference here is I1 R2. So that's going to be considered a positive potential drop. Because you're going with the, oh no, sorry, which way I'm searching? Look at that. I'm searching this way, so don't worry about it right now. What I said just now, ignore. We are searching in this direction. So when I search in this direction, I'm going against the current over here. So I'm going this way. You see that? The current is coming from the other direction. So what kind of potential difference is going to be here? Minus I1 R1. And then keep going along this loop. There's nothing here. What is here? Plus I2 R3. Why plus? Because my search direction and the current direction are together. So if you're searching along the current, it's going to be positive. If you're searching against the current, it's negative. Keep that rule. And then once you come here, this is going to be against the current, so it's minus I1 R2. And then equal to 0 because you reach starting point. So this is how you set up equations for each loop. You can set up 2 equations, and 2 is enough. Because how many current variables are there? 2. So all you need is two equations. You don't need to make one equation for this, one equation for this, one equation for the whole loop. You will need the third one only if you had taken it as I1, I2, I3. If you're taking it like that, then you need all the equations. So the number of equations you're looking for, the number of loops you're going to search in depends on how many variables you have on the board. You get it? That's Kirchhoff's second law in application. Now let's solve some problems. There are some circuits that you cannot do anything with. You cannot simplify the circuit any further. And those are the circuits that will require Kirchhoff's laws. Let's do this question. The circuit, I'm going to draw the circuit, and the answers that you're expected to say is just increases, decreases, or stays the same, like that. Here's the circuit. It's a good one. That's EMF. Now, actual lettering for EMF is something like that. You'll see it in textbooks. I don't like those kind of E's, and that's why I'm just writing E. What difference it's going to make. I know this is going to be electric field in the electric fields chapter, but when you're putting that E next to a battery, it is the EMF of the battery. The symbol for EMF is a kind of special E. So here's the circuit. There are some points. That's the ammeter. R1. R2, R3. R4, R5, R6. R4. What are those arrows? It's a variable. That's your circuit. Okay. Now the questions are these. So you can actually answer it as I describe the questions. Ready? Draw the circuit first. R7, R2, R5 and R7 are variable resistors. R2, R5 and R7 are variable resistors. That's why the arrows are there. And that's the EMF. The first one says this: if R7 increases, the potential difference between A and E, what happens to it? Assume that no resistance is there in this and this. In other words, there is no resistance for the ammeter, ideal. There is no resistance here, internal resistance 0. Okay? Assume that part of it. No internal resistance, no resistance for the ammeter. The question says, if R7 increases, what will happen to the potential difference between A and E? Where is A? A is here, and E is right there. If R7 increases, what will happen to the potential difference between A and E? All is mentioned is R7 is increased. Any answer? Well, there are only 3 answers possible, so you'll be at least 33% probability getting it there. Yeah,
Doesn't it stay the same?
it stays the same. Why?
Because the EMF still needs to measure.
Exactly. From here to here is purely the EMF, because I said there's no internal resistance, there's nothing for this. And so this R7 is increased. So if this is increased, yes, the current through the entire thing is going to decrease, but it's not going to do anything to this or this, because there's no internal resistance, there's no ammeter resistance. So the EMF is what is going to be measured across here and here, so that is not going to change. Right? The next question says, if R7 increases, the potential difference between A and E, what will happen to them? If this ammeter and this EMF, they have resistances. If this has resistance and this has resistance, what will happen if the resistance, if this one is increased? If R7 goes up, what will happen to the potential? If R7 goes up, what will happen to the VAE? That's the question. If R7 increases, this increases, what will happen to the overall resistance? Increases. What will happen to the current? Decreases. So remember that part of it. The overall current is going to decrease compared to before. The overall current decreases compared to before. And so what will happen to the potential difference between these two is the question. Yes?
It'll increase.
It will increase. Why? Any reason?
Yeah, so when you lower, or when you have a lower current flowing through the battery, or through that section, then the resistance lowers, so you get a greater potential difference across the...
Yeah, so what is happening is if this has a resistance and this has a resistance, there is a potential drop created in them. That is why the voltmeter here should read less than the EMF. But now when you increase the resistance, the current which was making that drop reduced. And therefore the drop reduced also. So you are expecting to get a higher voltage here. Make sense? So when the internal drop reduces, the external drop becomes higher. Simple as that. When the internal drop reduces, the external drop is higher. The next question says, if R7 increases, the voltage drop across R4 is what? If R7 increases, what's the voltage drop across 4? 4 is right there. If R7 increases, what will happen to the potential difference across just the 4? What are the answers? Any answers from here? Yes, Dominic.
It's going to decrease
Reason?
because the current is going to get smaller because R7 increases.
Yep. Because R7 increases, the current here becomes smaller, so what? So the current here is smaller, and that smaller current is going to be distributed kind of evenly. So whatever share was going through here, it will be having a slightly smaller share now. So therefore the potential difference across R4 is less. The next one, the fourth part, is if R2 decreases, the current through R1, what? R2 decreases. Here's R2. They're not going to talk about R3 decreasing and all that because that's not a variable resistance, but this is variable. So if R2 decreases, what happens to the current through R1? R1. Where's right? Where's R1? Oh, here. R1 is right there. What will happen to the current here? Yes, Ryan.
Will it increase?
Reasoning.
Because when the potential difference is supposed to stay the same, if the resistance goes down, then the current has to go up to accommodate for that.
Yep. So when this resistance went down, the equivalent resistance of this will also go down. When the equivalent resistance of this goes down, the equivalent resistance of the whole circuit goes down. That will make the current go in this one higher, right? And therefore there will be more drop across the R1. So the thing is supposed to go up. Oh, they're only asking the current. The current goes up. The fifth part. If R2 decreases, the current through R6 becomes what? If R2 decreases, the current through R6. If R2 decreases, the current through R6 becomes what? If R2 decreases, the current through R6 becomes what? Yeah.
Increases.
Why?
Because the current is more because the resistance dropped.
The current here, when the resistance went down, the equivalent resistance also went down. That will increase the current. When that increases the current through this section and this section and this section, all of them are supposed to increase. Good. That's one part. The next part says if R2 decreases, the current through R3 becomes what? If R2 decreases, the current through R3 becomes what? R3 is right there. If the current through R2 decreases, the current through R3 becomes what? This may be a little tricky, but just see if you can answer it. If R2 decreases, the current through R3 becomes what? Yes, again.
It should decrease, right?
Why?
Because there's less resistance going through R2, so more current is going to go through R2.
You can say that, but won't the entire current also increase?
Yeah. So will it stay the same?
So will it stay the same? You need to lock your answer saying that, yeah, this is the answer and this is the reason. You can't have a little, it may stay the same, yeah.
Does R2 decrease equal resistance for the parallel also decrease, and so the drop will decrease, and so the current will decrease.
That is correct. Also, see, when R2 went down, the equivalent resistance of the whole thing is going down. And therefore, more potential drop is going to take place outside, not here. So the potential difference across all of these two is going to decrease, and that means the current is going to be smaller. Next one, if R5 increases, you can write these things down so you can look into it later. If R5 increases, what will happen to the voltage drop across R2? If R5 increases, what will happen to the voltage across R2. R5 increases. What happens to the potential difference across this? Yeah.
Should it not change?
It changes. Yeah,
It's gonna go down.
it's going to go down. You can look into it and reason it out.